Video 6.6 Intermolecular Forces. And just what are those? Well, the forces of attraction between molecules. Do not confuse these intramolecular forces that we have been talking about. Examples of covalent bonds or ionic bonds occur in the molecule itself. Now we want to look at, we have larger compounds and how these forces between the molecules hold each other together. A short video here does a great job detailing the properties of these bonds as well as the three major types of forces that you need to know.
Intermolecular forces are the forces in between molecules. In particular, we're talking about the attractive forces. The attractive forces between molecules is really what ends up governing all physical properties. And when I say physical properties, I mean boiling point, melting point, viscosity, surface tension, stuff like that are physical properties. And it's really governed by how strongly these molecules are stuck together. Turns out a lot of these forces also affect the way chemicals react, because a lot of these same forces in the way chemicals come together, and then if you get them together, you have the possibility of a chemical reaction. We generally cover three basic intermolecular forces that we give three distinct names. The differences are really pretty subtle. It all comes down to the difference of a positive charge and a negative charge. That's really what the attractive force is about. So you have positive and you have negative. The more positive it is, the more negative it is, the stronger the force. This is simply Coulombic attraction. Positive attracts negative. Degrees of this. It's just a matter of how positive and how negative. Most molecules, being neutral species, do not have full positives and full negatives on them. That tends to be the world of ionic molecules. So we're constantly writing partial positive and partial negative. We even have the way we symbolize it on paper, which you should be used to as these partial positive and partial negative charges. Matter of fact, if you can get enough distribution within your molecule to where you have a positive charge on one side and negative charge on the other, you can get what we call a polar molecule. A permanent dipole is a polar molecule. And if you have a permanent dipole, you're going to have a setup within the molecule where you always have partial positive, you always have partial negative. And those are going to get together. That's called dipole. Longest interaction you can have with hydrogen being the partial positive part of this molecule. Anytime hydrogen is covalently bound to a very electronegative element, and I'll be specific here, it has to be bound to fluorine, oxygen, or nitrogen. And when it is, it becomes so partial positive, and the oxygen or nitrogen or fluorine becomes so partial negative that you get an even higher amount of attraction. So we go ahead and classify that in its own class. We call it hydrogen bonding, but it's really just dipole-dipole interaction, just up a notch. At the low end of the scale are nonpolar molecules. Now, nonpolar molecules are molecules that have no dipole moment whatsoever. They usually are nonpolar due to symmetry arguments, meaning that whatever you argue pointing one way, there's the opposite way covered somewhere else on the molecule. So all the symmetry wipes out the polarity of the molecule. Good example of this is carbon tetrachloride. Carbon tetrachloride has four very polar carbon-chlorine bonds, but they all nullify each other as far as distribution of charge. So it's a nonpolar molecule. However, it will attract another carbon tetrachloride molecule. They do stick. It is a liquid, so there's definitely forces there. So what are they? They're dispersion forces, and they are based on what we say are temporary dipole moments. Temporary dipole moments is when the electrons within the whole molecule are in such flux that at any one point in time, you're going to catch it with a slight positive end and a slight negative. And another molecule is going to get caught in that same time, and there's going to be an attraction there. This will change over time and time again in very fast time frame, yet the attraction is there. So it's a very slight attraction. It's not nearly as strong as a permanent dipole, but that's what we call dispersion forces. So that's all three forces together there. We've got hydrogen bonding up at the top, right under dipole-dipole interaction, and a little bit below that, we've got dispersion forces. Those are the three major intermolecular forces at play with all molecular substances.
The last force that was mentioned in that brief video, talking about London dispersion forces. I want to clear up here as it is a little difficult to explain exactly what that is. But in every molecule, electrons are always moving around in that molecule. At some point, they actually end up on the same side, which creates a temporary dipole. Remember, partial negative and a partial positive side. This basically induces another temporary dipole in the molecule beside it, and you have a partial negative to a partial positive attraction between the molecules. That is London dispersion force. I want to look at a short animation that will again hopefully help clarify this just even more for us. So here's our animation that is going to show us a little bit about what exactly a London dispersion force is. Right here, imagine these spheres as molecules within, this would most represent a solid. This is electron density. So it's showing the region here as to where we have the most electrons concentrated at this moment in time. Now, at some point, part of the molecule may have more electrons located on one end than the other. Partial negative to partial positive charge. This will affect the charges and the electrons on the other molecules. As this is partially negative here, negatives and negatives repel, it's going to repel the electrons on this molecule and the ones surrounding it to move their places around their molecule. So as this happens, we have an induced dipole. We've induced this molecule beside it to become partial positive here, partial negative here. Up here, partial negative here, partial positive. This is what the London dispersion force is.